Okay, in this video, we will introduce LSTM, short for long short-term memory, and also RNN, recurrent neural network. Although RNN and LSTM is not the core concept of autoregressive models, it is quite natural to implement autoregressive model using an RNN or an LSTM. And also, we are actually going to implement one of the language model using autoregressive language model using LSTM next week. So it seems a good time to introduce the concept of RNN this week. Also, it also connected to the large language model that we are going to introduce later in this course. Okay, so in this video, most of content, or actually all of the contents, are taken from a blog post, an essay. You can follow this link. This one, although it's kind of dated, this is an article from 2015, but it is really excellently written. I always recommend this article to students when we discussed about the RNN and the STM. So I always recommend the students read this article in order to understand how the LSTM and RNN works. So all of the image in this slide are taken from the website, the blog post. So the slides only serve as tools to introduce the contents in this article. So all credits goes back to the original author, Colette. So okay, for example, this one is taken from the article, and this one is in fact a pretty good diagram of showing what an RNN or a basic structure of RNN is. So LSTM is essentially a type of RNN. So what is RNN? So in contrast to feed-forward network, the main difference is that for the computation graph, the RNN has a loop in its computation. I can say the computation graph or a computation process. So for the usual, the vanilla, typical simple feed-forward network, or let's say MLP, multi-layer perception, it usually works sequentially. That is, first we have an input. We have an input vector, a vector of input data, and it passes through the first layer, and the output of the first layer, or maybe after an activation function, it goes to the second layer, and the output of the second layer go to the third one. So the computation flow is layer by layer, one by one, sequentially. So although in modern architecture of neural networks, it usually has some skip connection. So maybe we use the output of first layer and directly to use as an input or part of input of the third layer or the later layers. But still, for every operation, we can sort the layers one by one, and the input of a layer is dependent on the results of previous layers. So there's no loop. So in RNN, we have a loop right here. So how does it even compute if we have a loop in our neural network? It doesn't make much sense, right? So in fact, there are several ways help us to understand the actual work, the computation flow of RNN. Okay, so we have three different three different fields to see what does it really means by this loop of computation. Okay, this kind of perspective helps you to understand how RNN works. So the first one is that you can actually imagine this A or this green box as a black box, or you can imagine it. I mean, it is a black. It can be implemented by any kind of architecture, but in particular, it can be implemented by a MLP, by a standard feed-forward neural network. There's no loop inside. So the first perspective is you can view it as just a black box or a standard neural network with two input and two outputs. So you may see that for the first one here, there's just single input. However, there are actually a hidden or initial input that we assume that is here, but it is perhaps it's just all zeros. It is every input is a vector, also it may be a zero vector. And for the other input, just like the autoregressive model, we typically assume the input is a sequence. So the whole input is a sequence. We have a x0, x1, x2, x3, x4, and so on. But for the first iteration or the first step, we only take the first element of the sequence x0 as the input. So we have actually two inputs. The initial one, the initial state, we can call it a state, and input from the sequence, the first element. So because this one is either a black box or you can consider it as a neural network, it takes two input. Then after some computation, we have two output. One is the usual output that you can explicitly see as a output, the final output, or an output that you can use for later computation. The other output is a spatial one, which is the state output. This step output is used as the input of the next iteration, or for the next step. Let's just call it a step. For the next step, it also requires two input. One is taken, we simply take the second element of the sequence. And for the other spatial input, we take the output, the state output of the first step, and use it as one of the input of the second step. And for the second step, you also have two outputs. One is the usual or the real output, and the other one is the state output. And again, the third step, you need two outputs. One is taken from the real input, the sequence, and the other one is generated by the second step. And you can see that you can keep going and do all the computation. And one good thing to feel it this way is because you can easily connect it, this concept into the autoregressive models that we introduced. So for example, if we are expecting the first output, that is H0, H0, to be equal to x1, and for the output of the second step, that is we taken the input for the first two elements, x0 and x1, and if we are expecting it to output some x2, and the third output is expected to be x3, and so on. This is exactly the autoregressive model. So we can actually consider a model that has two input and two output. The one input, let's call it the real input and the real output, is corresponded to the input and output of the autoregressive model, and the other pair of input output is a spatial kind of input and output. We can call it the state. So we can chain all the computation together by using this simple either a black box or maybe a neural network together and do the auto-regressive model. So this one seems to be pretty. So that's why we consider the LSTM to be a very natural implementation of an autoregressive model. However, an RNN does not necessary to be an autoregressive model. It can take any sequence as an input and output any sequence that you want. For example, it can be applied to a machine translation task. So the input is not the same as the output. The input may be an English sentence, and the output may be the equivalent Japanese sentence. And sometimes you don't even want your output to be a sequence. For example, we want to do a classification on a sentence, on an English sentence. In this case, we only need to, maybe we want to classify this sentence as a positive meaning or has a negative meaning. So you only need one output. In this case, we have several ways to aggregate this output sequence into one output. The usual ways are maybe we can take the last one. Taking the last one is a way to is a kind of aggregation, and maybe we take a mean. So we have a sequence of values. We take the summation, or we take the mean, or we take the maxima one, or the least one, the largest one or the least one. So we can do, depends on the application, you do some kind of aggregation on the output. So that's the usual way of applying RN to the task. But it's typically taken a sequence of input. I take a sequence as the input of this RN model. Okay, so that's one way of viewing the RNN network. So the other way is, the other point of view is to treat this RNN, this neural network, as pretty much like the usual neural network, except it has a memory, which is also called the state. So it's still got one input and one output, but this, we don't necessarily to chain them together in a line, but you can consider this one is a neural network, but it has some kind of memory. Of course, the implementation, if you we are actually use the output of the first step. It has to be stored in the computer memory or somewhere. But you can view it as a memory cell in this neural network as part of a neural network. It's just if you actually want to implement, one way to implement it is using the first kind of perspective to see it. It is sort of we output a state into somewhere, and for the next computation, we always retrieve the memory from where the state has been stored. But if you view the whole thing as a whole, then it can be viewed as a neural network which has a memory. The memory has terminology to call the memory is state. A good analogy, if you are familiar with the functional programming, it is the usual neural network is kind of like a pure function, and RNN is like a function with side effect. So if you are familiar with functional programming, so you can kind of feeling that RNN is a non-pure function. That is a function with side effect, which means every time when we say a pure function, it's kind of like a mathematic function. Which means that given an input, let's call a function f. So every time you want to compute f, like f3, just for example, you will always get something the same. Like if first time you compute f3, you got 5. The next time you compute f3, you will always get 5. No matter when you feed the 3 into this function, you will always get 5. So there are some benefit of assuming this behavior of a function. This kind of function we call a pure function. There are some benefit of assumption of a function is being pure. So for example, we can have more freely to do the compiler optimizations, or maybe we can kind of catch the result. If the computation is expensive, we kind of store the result into memory, so we don't have to compute it again because it will always return the same value. However, a lot of functions like a computer, if you use some variable like a static variable, or in maybe even global variable, or maybe it interact with some device, this function may not be pure. So there's some distinction between a function being pure or not. So RNN can be considered a neural network with memory with side effect. Also, that's a second view that you can make a distinction between RNN and some neural network that is not recurrent. A third view is that you can view this whole thing as a big neural network, maybe just a plain MLP, except it is a very special kind of MLP. So how special it is? The first, the whole H can be considered as the output of a neural network, and the whole X, the whole sequence, if you consider it concate the whole element, every element together in this sequence, and we are consider this sequence has a finite and predeterministic, predefined length, a fixed length. So the whole thing can be considered as the input of a neural network, and the whole H sequence is the output. So this one is just simple. If we just chain them together, which we call the unrolled unrolled recurrent neural network. If you just feel them make the iteration to be flattened or unrolled, then it is just a simple neural network with this x as an input and h as an output. The spatial properties of this neural network is that you can see it share a lot of weight between the layers. In fact, if you consider this one is the first layer, this one is the second, this one is the third, and this one is the last one. So maybe just a layer, it may be a block, but we just call it layer for the simplicity. So you can see that every layer has exactly the same structure and the same weight. They share the weight. So one way to feel the unrolled recurrent neural network is it is a big MLP with identical layers, or the layers are actually shared. Okay. Okay, by viewing this as a huge network, so the first strange thing or special thing is it share the weight. So each layers are identical and they share, they have identical structure and identical weight. The other thing is it doesn't feed the input from the first layer. The input are fed element by element, one by one, to each layers, and it doesn't output from the last layer. It progressively output from each of the layer. So that's all. But still, although this architecture or structure of the MLT is kind of unusual or strange or very special, but still, essentially, it is, if you just unroll it, it is just can be considered one type of MLP. So in this point of view, we know that how to actually train this neural network, because we can simply train neural network like the other MLP or other feed-forward neural networks using exactly the same way, which is gradient descent and back populations model algorithms. We can use the exactly same way to train it. So that is exactly the how we train, or there are many ways to train the RNN, but the most common way to do that is just unroll it, and then we can view it as MLP, and we can simply train this neural network. Okay. So LSTM is just a special kind of recurrent neural network. It actually fixes one of the big issues of the recurrent network that has. So what is the issue? The issue is it is very difficult to train MLP. I mean not MLP, RNN. So as we mentioned before, this is how we train the neural network. But for many times, many situations, the output, one of the output maybe depends on some of the previous input. So for example, we probably are expecting that H3 is depend on X1 and X0. So we probably have to depend on the output. If this output is not expected, we might want to adjust the weight in A. according to what the x1 and the x0 is. However, if this output has a very long distance between the input, it might be very difficult to do the training, because their relation has been passed through a lot of operations. Although in theory, because gradient descent can find the best weight, so in theory, sooner or later, or if our optimization algorithm works, it will learn the best weight, the optimal weight that can output the expected output from any sequence from the data set. However, in practice, it is very difficult to train the RNN. It will usually cause some gradient finish problems when we train the RNN. So we need some kind of ways to avoid the gradient finish issues. So this one is the standard RNN architecture. So let's investigate into the architecture and the structure and see what happened when we train these networks. You see that when we do the back propagation, so we have some loss function applied to, say, this HT, and we do a back propagation through this backwards through this arrow path. So if we wish to go back to like xt minus 1, the path will be something like from here, and you can follow the red dot, and you go back here and go back here. So along this way, there are some parameters interact with this input and do some computations. So we use the loss function and to compute the gradient and do the back progression and update the corresponding weight. However, you can see that we'll pass through one tangent edge, hyperbolic tangent, and go back to here, we will face another one here. So if the relation is very has a very long length or very distant relation, then it will pass through quite a few or a lot of hyperbolic tangent. If you are not very familiar with this function, this is kind of like a sigmoid. Sigmoid is a function that pretty much looks like a step function. It will be 0 when it is a function. If you input negative numbers into this function, into sigmoid function, it will usually output something close to 0. If you input a positive function, positive numbers into this sigmoid function, it will output something close to 1. So it is not exactly a step function, but it is a smooth function, but it will be, you can feel it as a smoothed step function. When I say step function, I mean it is 0 when x is negative, and it becomes 1 when x becomes positive. So it looks like a step from 0 to 1, it jump to there. Sigmoid is a smoothed step function. So basically, it maps the whole real numbers, whole real line, real numbers, into a small range between 0 and 1. So a lot of part of the sigmoid function become very, very flat. So the gradient it's very close to 0 for most of its domain. Because the gradient is usually very small. The reason the gradient is small is because it first, it is a monotonic increasing function, and we compress the whole real line into a small range, 0 and 1. So the increation, the function is an increasing function, monotonic increasing function, but there's not very much room for it to actually increase. So for most of the time, for most of the domain, it increases very slowly. So the gradient has to be very small. And after it go back to another, if we have a lot of sigmoids, chain them together, the gradient will, the first one will make it very small, and the second one will make it even smaller. So the gradient finish to 0 very, very fast. Because the gradient is very, very small, so the gradient descent algorithm doesn't work very well because it can only update very, very small amount of the weight, can only adjust or change the amount of the weight only by a very small amount of value. It is because the gradient descent based method usually update the weight by the gradient itself. So if the gradient is very, very small, then the weight cannot move very much. Okay, so what about the hyperbolic tangent, or we just simply call it tangent H? The hyperbolic tangent is pretty much the same as the sigmoid function. The only difference is that it is from -1 to 1. It's still kind of like a step function, but it does not jump that unlike the sigmoid function is from 0 to 1. Sigmoid function is from 0 to 1, but hyperbolic tangent is from -2 to 1. Other than this, from 0 to 1 and the -1, other than this, they are pretty much the same. They are actually, you can consider it as some kind of linear transformation of the sigmoid. So it can be considered as a kind of variation of sigmoid. So it shares the same issues as the sigmoid. Like I mean, the same issue means the gradient finish problem. So how do we actually it not only for the LSTM or RNN, I mean, sorry, I'm not LSTM, I mean RNN. In sigmoid is one of the typical or most common or most popular activation used for neural network in time before maybe 2005 or 2000s. So if a neural network with sigmoid as activation function and it has many layers, that means it's very deep, then it also has the same issue, which I mean the gradient finish problem. So there are many ways to solve this problem. One way for the very deep neural network is to use a skip connection, to use a rest block, or to use batch normalization. And one of the early methods to solve that is to use ReRO instead of sigmoid as the activation. However, for the time for the LSTM, I don't think that ReRO is the most popular activation, or not the most popular. It may be considered as a poorly working activation function, maybe, but it is not usually used by neural network So the LSTM still using sigmoid and hyperbolic tangent as its activation function. It uses another way to solve the gradient finish issue. So this one is the architecture of the LSTM cell, or for this cell. You can immediately see some difference. One is that not only one state, input and output, between the iterations or between the steps, there are actually two. So we actually feel the upper one as a long-term memory and the bottom one as a short-term memory. So we're expecting that at least for the long-term memory, the gradient finish issues might be actually solved or at least handled differently. So we are going to focus on the first. We are going to focus on the long-term memory, which we will call it as a cell state. This is actually the cell state right here. So in order to understand this computation graph, so we focus on the long-term memory, which is a cell state. It's equal to C cell state. One of the major component, we can call it as a gate. So the gate is in fact a way to control what pass through. We are going to apply it on the cell state, like the long-term memory, and also on other part. But this one is called the gate. So for example, let's consider about the long-term memory. So I have a memory here. The memory is you can consider memory. The memory is a vector. So maybe let's consider a vector of length 10. So you can consider we have 10 numbers or 10 boxes that contains, each box contains a number. So the sigmoid is the gate. The gate also has 10 numbers, but because it is passed through activation function sigmoid, so each of the output is between 0 and 1. And to simplify the computation, you first imagine each output is either 0 or 1. Although the sigmoid does not output something 0 and 1, because we only fit into some real number, not negative infinity or infinity. So it will not output exactly 0 and 1. But for most of the number, the output of the sigmoid is very close to 0 or very close to 1. So maybe it is 0.99 or 0.01. So for simplicity, we actually imagine it to be the output of sigmoid to be like 0 or 1. Kind of like what we imagine of the output of softmax. Because we usually match the target of the softmax is usually a 1 hot, which contains only 0 and 1. But the output of softmax is never 0 and 1. So for the simplicity, the sake of simplicity, imagine that our output is either 0 or 1. So because we have a memory of 10 numbers, 10 boxes, so the output tells which box we should keep and which box we need to forget. So for example, by using we have one means we want to keep the box, and 0 means we want to forget about the numbers in that box. So this is actually the element-wise multiplication. So 1 times something, it remains, and 0 times something becomes 0, so that we forget the numbers in that box. Okay, so it kind of, if we feel it like this way, it kind of like a rerule. Rerule actually keep anything that is positive and forget or ignore anything that is negative, because anything below 0 we cut them out to be 0. So for real, you can feel kind of like this one, but real keep anything that is positive and forget anything that is negative. Except real, the forget or memorize things, keep or throw away only depends on the value of the number in the box. However, in this one, the decision on whether to keep or throw away the number in the box, keep or forget the number in the box, is dependent on other independent factor that is computed by other means. So we use this get to decide which box we wish to keep and which box we want to forget. Of course, the output of sigmoid is not exactly 0 and 1. It's something close to 0 or close to 1. Or maybe in some case, it may not be something like 0.3 or 0.5, and we do not consider it as some number close to 1 or close to 0. But it is some number between 0 and 1. And typically, it will has a number very close to 0 or very close to 1. So we does not, when we keep something, we usually keep most of it. When we forget something, we do not forget it totally. We keep some part of it, just a very, very little part of it, like 0.01 part of it. And in some cases, we might forget half of it and keep half of it. So that is what the get does for this memory. Okay, so have the get operation in mind. So what does the LSTM do? So first, we take the input x, that is a real input, and the state input, that is from the short, you can call it a short-term memory. From short-term memory, it turns out the short-term memory will be the output. In this situation, in this setting, it will be the output of the last cell. But anyway, just call it xt and ht minus 1. We use xt and ht minus 1 to compute a get. That we call this get a forget get. So we're used to decide which part of the long-term memory to be kept and which part of the long-term memory to be forget. And you can imagine there are many ways to compute the get. However, the typical one is using a very simple network to do so. So this is in fact just a affine transformation, and we of course we use a sigmoid as our activation function. Okay, so this one is just a simple computation of what the get is, and we also compute. Not only we try to forget something, we want to update our long-term memory, C. So to compute, what kind of memory we want to update? So the memory itself is also depends on xt and ht minus 1. So we also do a very simple affine transformation right here, and we use hyperbolic tangent as our activation function to compute our content. But we do not simply update the memory to the new one. We compute another get, and again, the get is computed using another weight, another parameters, but also still a fine transformation, and still using, still depends only on xt and ht minus 1. We compute a gate right here. We use this gate to decide which part of this content is going to be updated into a new memory, into the long-term memory. So you may wonder, why not we just, because we already know which part we are going to forget and which part we are going to keep, why not just using the 1 minus ft as our gate? Because, okay, so if suppose this forget gate tell us to, okay, you can throw away the first box, forget the first box and the third box. It seems that we only need to update the first box and the third box and keep the rest of box like 2, 4, 5, 6, 7, 8, 9, 10. All these boxes are kept because we don't need to update it. The thing is that you can imagine a case that we wish to compute the mean or the summation of this sequence. So maybe a box is keep the summation of all the x0, summation of x0, x1, x2, x3, x4. In this case, although we are still wish to remember or keep the say the first box, we still want to update the first box. So they are not necessary. I mean, it is not necessarily a case that when we forget the first box, we have to update the first box. And if we are keeping the first box, we do not want to keep the first box. So there might be all combinations like keeping the first and update it, keeping the first and do not update it, forget the first and update it, and forget the first and do not update it. So all this combination may have some application or meanings, practical meanings that we wish it to, practical behaviors we wish it to have. So we keep it open. So we use another gate to do the to decide which box need to be updated and which box does not. Okay, so after these two guys doing, we can have a new long-term memory CT of updated from CT-1, keep something and forget something, and update something and do not update something, and we got a new long-term memory right here. So it is a linear combination of the original memory and the new one that is composed by xt and ht-1. Okay, so how about the output ht here and the new short-term memory? So we use the xt and the ht-1 once again to control a new gate, which we call the output gate, and use this output gate to apply to the long-term memory. This long-term memory is passing through hyperbolic tangent first to kind of compress it into -1 and 1. And we use the gate to determine what part or how much of each part has to be considered as the output. So basically we have 3 different gates, and the major memory is the long-term memory CT, and the output is depend on CT and some kind of gate to control the proportion that need to be output. So this is one of the basic architecture of LSTM. keep in mind that there are many different variations, and a lot of variations are very popular. So one of the variation is the peephole. So the basic idea is why the gate is only depend on xt and ht minus 1. Why not depend on ct minus 1? Because this one is one of the major memory, that major state, the primary state that we have so far. So why not use it to decide our gate? Although we know that ht minus 1 is very close to ct minus 1. It is ct minus 1 passed through some hyperbolic tangent and using some gate to control the proportion that of the output. But still, this one contains the full information. So why not simply use it directly? So this is the peephole. There are other motivation of this architecture design, but basically, I think it is quite straightforward to ask why not using ct-1 or ct as an input to decide gate. So of course, after the ct is updated, all we have is just ct, not a ct-1. So we use the ct to update this gate. If you really want to use ct-1 to do so, I guess you can still use that. You just have another copy of ct-1 and maybe you use that ct-1, ht-1, xt together to decide what the gate should be, to decide the output gate. So that's doable, but I mean the standard peephole is look like this one, and I think this one is so popular. I think I see this one more often than the one without peephole. So another way variation is something we have already discussed before, that why not if we we forget the box 1 and the box 3, maybe we just want to update the box 1 and the box 3. So if the you are imagining, if you consider your computation is something like this one, you don't need to do the summation or the things like that. You are keeping a memory that either to keep the old one or using the new one. If that is some kind of the algorithm that is in your mind, then maybe we can just we do not need to use separate. We do not need to compute the new gate independently. Maybe we just use the complement of this gate. So this one is coupled forget and the input gate. You can so this one also is very straightforward and kind of one of the trivial or obvious approach that we may have to modify our networks. Like we has discussed before, there's one direction to make the network more complicated. That is, we can replace the affine transformation into a more complicated networks. However, another way to do that is to simplify the network. I think gate recurrent neural network, GRU, or in short GRU, is one way to simplify the LSTM and make it still very powerful. And sometimes people may consider it is more powerful or more useful than LSTM. So you can see that it only has one, like the RNN, it only has one state output, not two, not long and short-term memory. It's just one output, and a lot of things is simplified. So I'm not going into detail about this this architecture design, but it is very popular. It might be my first choice if I wish to use. I would simply use, if I have a choice between LCM and the GRU, and I only have one choice, I probably will choose GRU. That is what I one way to say that GRU is very important and very popular. Okay, there are other variations. So always and really, I mean really a lot. So there's always you need to actually look what the variations that people are using. If you are reading a paper, just look through what variation people are using, and you can also go to the document of the frameworks like PyTorch or TensorFlow or Keras, and to see there are some popular variations and the options that they are applied to. You can they are always presented as a Q argument or some kind of argument that you can modify or change the uh, as a hyperparameter to design the recurrent unit. And another popular variant of the LSTM is bidirectional LSTM. We're going to introduce this when we talk about the pixel RNN. So it will use something called bidirectional LSTM. So that's all about this part.